Okay, welcome to lecture 4 of this lecture series on quantum field theory. I'll start with a very quick recap of what we did last time on the last video, just to keep our minds fresh. So last time we started to see what a path integral is. Right? So we started with this propagator, which is an amplitude of transition from one quantum state to another, and we found a way to calculate these propagators in terms of a very different integral, right? So what I did was to write the propagator in this way and then insert many intermediate times between the time, the initial and the final time for which I'm calculating this transition, right? And for each of those times I have these completeness relations of these moving frame states, and that allows me to write the propagator in terms of a sum over these many different trajectories here. I'm integrating on each of these coordinates, right? So I'm basically integrating, summing over, but in a continuous way, over all the possible paths that the system could take between the state characterized by Q and T and the final state characterized by Q prime and T prime, right? And we invented symbols for these integrals and wrote the propagator in terms of these integrals, which are right here. Once I also include the momentum integrals, right? So I have shown that you can actually also include momentum states in the middle, right? And then the propagator ended up being written in terms of a path integral of the exponential of classical functions, right? This is the classical Hamiltonian and some momenta and speed of classical coordinates. And now I have some quantum, some variable that encodes the quantum behavior of the system, writes in terms of classical functions, but I'm doing the path integral to get from one to another. Then I show that you can actually, for some systems where the Hamiltonian can be put in this way, just a kinetic plus a potential term, then you can actually do the integral in momenta and get to this very important expression right here, in which now the propagator is written as just the path integral of the exponential of the action, right? Which is quite amazing, considering this is again a classical function, and and because you're writing in this way, you can see that close to the extreme of this action, right? The action will be varying very slowly, so there will be constructive interference of all paths that are close to that extreme of the action, and we know that these paths are the classical solutions for this. The classical path, right, is obtained by the principle of extreme action. So that means that this expression is taking into consideration that the system will follow a classical path, but with many quantum fluctuations around it, right? So essentially, the quantum behavior comes from the path integral, right? And the weight or the phase of each of these different paths will be determined by the action. Then I took this correlator, which is just transition between two states, and I generalized the object to more complicated correlation functions. Right? The propagator is just a particular case of a bigger class of functions, which I'm calling now the correlation functions or correlators. And then I did the same. Right? Just the correlators will have a number of operators in the middle here. So I'm again considering a transition between two states, but I'm inserting a certain number of operators in the middle. And then I have shown that you can actually do the same as I did before, inserting the slices of time here and here, and writing this in terms of a path integral. But something very interesting happens when you do that with more than one operator. And what I did show was that when you do that, the path integral ends up being the time ordered product of these operators in here. So I can write it. I can write the path integral in this way. So if I want a correlator with more than one operator, I can write it like this in the path integral, but the path integral ends up being the time ordered product of these operators, and that's what I'm calling a correlator. So here I wrote the more general expression for correlators. So a correlator will be the time ordered product of operators between these two states, or the path integral. So you have two ways of calculating. I can go the canonical way and just figure out the properties of these operators and act with them on the states to the left and to the right and calculate this, or I can do the path integral. We'll soon see that these correlators, they encode all the information I need about a quantum field theory. If I suppose I knew exactly the form of all the correlators of a particular theory, I would know everything there is to know about it. Right? So they will show up again and again in the calculations we'll do in the course. In fact, what I want to show now is that you can encode this information of all. As I said, you would need to know the many possible endpoints. So you have correlators of 0-point correlators, 1-point, 2-point, 3-point functions. Right? You have many possible values for this variable n here. Right? But I can actually encode the information of all the correlators into one single generating function. Right? That's a pretty interesting thing, and will allow us later to make very interesting analogies with statistical mechanics. So let's take a look at what this generating function is. Right? So you could first, just to stay through something that is very well known to everyone, let's think of a set, right? A set of numbers an, right? So let's say instead of a set of functions that I have here, g0, g1, g2, I'm just for now focusing on a set of numbers that goes from a0 to a infinity, right? I can actually put all the information about this set on a function. I just have to write a polynomial, right? If I write something like f of x as the sum over all n, 1 over n factorial. This is become clear why I want this factorial soon. an, xn, just a polynomial on x. Everyone will agree that knowing this set of numbers is the same as knowing the coefficients for this polynomial. Right? In fact, I can take then some number of derivatives of this polynomial function, say 2 derivatives on x of this function, which I'll write a little bit more explicitly like that. a0 plus a1x plus half of a2x squared plus 1 over 6 a3x to the cube, and so on. Right? If I take a derivative, two derivatives in x of this function, what will happen? This is 0 because I'm taking two derivatives. Same here, that goes to 0. This one becomes just a2. This one becomes just a3x, and so on. Right? And then if I set x to 0, suppose after taking the derivatives, I set this auxiliary variable, right? X means nothing here. I'm really only interested in these coefficients. If I set x to 0, when I set x to 0 here, all terms but this one will die because there's powers of x multiplying every single other term, but this will be just a2. So I can extract any of the coefficients from the polynomial just doing derivatives. Right? That means I can write an as the n derivative of this function f of x with x equals 0, right? Just do n derivatives of f and then set x to 0, I get an. So I want to find a similar expression to this one that will give me these functions. But of course, these derivatives acting on a function give me numbers after these setting x to 0. What I want now is similar thing that will give me functions. And for that I will have to use functionals and functional derivatives. Right? So I'll define something here called generating functional, which will be equivalent to this f of x, but now I'll call it z of j. And these brackets here mean something, means this is a functional of j, and j are functions, not like a x here that is just a real number, right? They are functions too. Right? And I will define this as the sum. Let me get some more space here. The sum over n bigger than 0, right? Of a product of integrals that goes from dt1 to dtn. So I have in each term of the sum I have more and more integrals, right? I to the n factorial gn d1. And this is the endpoint function, right? The correlator that I have up here. Tn j, and these are just a product of these j functions n times, right? Big N, capital N times, right? Let me put a box around this and give it a name, because this function will be very important. Right? This is the generating functional. The thing to pay attention here is the parallels between these two expressions, right? Because this one looks very complicated, but it's actually almost the same as the simple one up here, right? So first, why the integrals? Why do we have these integrals here? Well, here I have just a product of numbers, right? There's a product here. And this, the product of these two functions, these functions by these ones, integrated is actually what I would call a scalar product between functions, right? The result does not depend on t. So in this vectorial space of functions, this would be the scalar product between g and some power of j, right? This is x to the n, and here I have n, now this time capital N, powers of j. And this variable is completely irrelevant, right? It's just a variable that I can exchange any time I want because it's integrated over. So the integrals together with this product makes for a scalar product of functions. And here I have a polynomial in j, just like I had for x there. The 1 over n factorial has exactly the same role it had here, because eventually I'll be differentiating towards these j's, right? And that will drop me factors, numerical factors that the n factorial is here to compensate, like he did for the second derivative here. And if I I mean, in the end I have j playing the role of the an, which is what I want, right? Essentially I can now extract Jn from here, doing derivatives in J. I'll define a little better what these derivatives are in a second, right? But and of course this is now a functional, not a function. Z is not a function of t, right? It's a function of J because it does not depend on t. T are integrated over, right? So what really changes the behavior of this functional is the shape of the J's, right? If I change what these functions J are, then I change the functional. The functional is then, once I do this calculation, it's just a number. But it encodes a whole lot of information. It has, in order to fully know Z, I have to know all the Gn, from G0 to G big, right? So that's the generating function. So how do I properly define derivatives that will extract me the endpoint correlators, which are here? So what we use is what is called a functional derivative, which I'll not properly define here. We'll just mention the properties and use it. But those of you that are really interested in seeing the definition of this thing in terms of limits, either go online and look for this name Frechet derivatives, which is what these things actually are, or there's also some additional material on my website, item D. So go in the site and look for additional material item D, and I have some derivation of these from a little more rigorous groundings, and there's references there if you're really interested. But for us, what really matters is that we'll define and use this symbol to define a derivative between functions, right? So essentially I can differentiate f in terms of another function, right? When they are the same but with different variables, the answer of this derivative is simple. It's just a Dirac delta function, right? If this would be a function of three-dimensional x and three-dimensional y, then this will be simply the Dirac delta for vectors x and y. For now, we're just sticking with functions of one variable, so this is what we need, right? And when you differentiate different functions, say I'm differentiating a g that can be written as a function of f of x in relation to f of y, right? These two variables are not important, right? So they can be different. In that case, I get again the delta x and y and the partial derivative of del g del f of f, calculated in the point where f is just the f of x, right? Of course, then since this is multiplying this Dirac delta, the whole thing will in the end depend only on y. So as you see, once I define these derivatives in terms of the partial derivative, that means that every other property will be the same. So the chain rule, product rule, everything you use to do in terms of derivatives will also work here. And again, I can now use this derivative to extract information about the endpoint correlators here, endpoint functions. So imagine I take that z of j up there and apply one functional derivative. I put a factor I here just to conceal these factors of I that I put on the definition here. You might ask, why did you put it in the definition in the first place? And that will be clear pretty soon. For now, just bear with me. I'll put an I here, there, right? And I need to differentiate in terms of j of some calculated at some point, let's say t bar, right? And then after applying the derivative, I set j equal to 0. It's the same way I did up here. It's pretty intuitive what will happen, right? So the first term in this sum, and the capital N here equal to 0, has no j's, so that one will be 0. All the terms with n bigger than 1, like n equal 2, n equal 3, and so on and so forth, will have a number of these j functions even after I differentiate. And when I set j to 0, they will all be 0. So the only term that will survive this procedure is the term with just one j, the term of the sum where n equals 1. So let's see how that term looks, right? So out of the whole sum, right, the only thing that will survive is this. So this is just the derivative, and now I'll put just one integral because I'm arguing that just the term with n equals 1 survives. There'll be an I here, 1 factorial, I mean, right, just for completeness sake. This I will go away as I was expecting it to. G1 of T1 and J of T1. Right? So the derivative goes inside here and hits this guy, making it a Dirac delta, right, of T, T1 T bar. So in the end, I'm left with the integral in T1, G1 of T1 delta of T bar minus T1, which is just G1 of T bar, as I expected, right? So I'm saying if I do the right number of derivatives in Z, I extract these correlators. In this case, I just did one derivative, so I extracted the 1 point function. And it is important to realize here, right? This guy is not depending on T1 to Tn, nor the answer is. The only dependence in T that appear here is because it was inserted by the fact, let me put this in colors because that's very important, is inserted by the fact that I put this T bar here. So the answer, this answer is a function that depends only on T bar because I'm putting the dependency in there. Right? It comes through the functional derivative and ends up here. The T1s and Tn's that are inside these integrals are completely mute variables. So, okay. Now I want to rewrite. So I hope that it's clear that I can extract the Gn by doing derivatives. If I do the second derivative, I'll extract information about G2 and so on and so forth. Now what I want to do is to rewrite this Z in a more enlightening way, because right now you could ask me, you exchange the problem of calculating these Gn's by the problem of calculating Z. But if the only way you have of calculating Z is actually figuring out Gn's one by one, then you gain nothing, right? You're just fooling around in a way to store that information, but you have to calculate G one by one, right? And the answer is no, and let's see why. So let's try to rewrite that Z in a different way. For that, I'll have to reorganize it. So let me get a copy of this down here. And let's reorganize this expression a bit to see what happens. The first thing I want to do is rewrite G of n in terms of its path integral definition. So let's copy this part, because this will just repeat itself. Also the j's, leave the j's here, and I'll rewrite G of n in terms of the path integral definition, which is just the integral of q exponential of the s of q of t1, q2, q of t2, t3, etc., all the way to tn. Right, so this is just G. It's the same as here, right? And now I want to reorganize these by grouping together all the variables that depend on the same time, these times that are integrated over in the expression. So let me repeat the sum. And now these I'll just group together with these and this. Right? And I'll take one of these i's. I have n of them, so I'll take one I together with each integral, right? And of course I can repeat this because I can group also for the second time, so I have also exactly the same expression for t2 and so on. And the only thing that is left here is I have to, in order to group these, right? Of course, I cannot take these q's outside this integral because it's integrated over q. So that integral. On the flip side, these guys can go in here because none of these depends on q, so they can go inside this integral. I can put the integral over here, right? And of course, I have still this exponential here, and this has many terms of the same. All of them look the same, right? I'm just grouping the functions q, and I forgot the n factorial. Let me leave it here for now. So the important thing to notice here, this is starting to look very familiar, right? If I again reorganize this just a little bit more, what I'll have is, let me repeat this part, bring that exponential over here, and actually let's bring this sum over here. And then, of course, these terms are all alike, right? Because these variables are mute, right? They don't mean anything. I can just exchange these variables by any arbitrary variable. So that means that I just have n times the same integral, right? This integral right here. And this sum is just the definition of the exponential. So I can rewrite this as and that's why I have this I here, right? Because it will be the complex exponential. So this will be just the exponential of qj. And so I can write this as, and now I'm grouping with this other exponential there. Which again is the scalar product between j and q in this vector space of functions. So you see, now I wrote this z of j in terms of a path integral of the action, right, of the exponential of the action, plus this extra term here, depending on j, right? And I'll name this part here as the action of q and j, or the action in the presence of sources. I'll talk about these sources later. For now, it's just a name, right? So I got finally a very important expression again. exponential I s of q j, where j is here just auxiliary function, but we'll see that in many physical systems j can actually have a physical meaning. Well, we'll get to that. For now, the important thing to notice here is now when I want to quantize a theory, what I usually know is the classical action. Right? I know a classical system, and I want to know the quantum behavior of that, the quantum analog of that classical system. Right? So what I know is the action of the classical system, which I can just plug here because this path integral uses the classical action. And then if I can actually calculate this integral, which I did already in the case, for instance, for the momentum integral, if I can calculate this integral, then I know z. And if I know z, I can just use functional derivatives to get all of the correlators for the theory. Right? I know that's still a little bit far off from getting the correlators to get observables. I have not defined yet how do you get observables from the correlators, but we'll get there. I'm just trying to build a main framework here that then we'll be able to use to get observables. And then of course now it's even easier to apply functional derivatives to get the correlators we want. I just have to notice that these will be derivatives acting on exponential, right? So, which are the easiest kind of derivatives. So if I do n derivatives on z of j, and remember I'm putting factors of I here. For each derivative there will be a factor of I. Just to conceal the i's that will drop from the exponential here when I differentiate, and in the end I put j equals 0. Right? It's easy to see that what happens is that for each of these derivatives I will come act on this exponential. Remember, the exponential has a term like this, which is just a scalar product of j and q. So the exponential, the derivative of the exponential will be the exponential itself, but then you have to do the derivative of this part that has a j, which will be just q. Right? So you end up with the exponential again, and let me do proper exponential here, and a number of q's in the same variables I introduce here. And that, of course, is just the definition in terms of path integrals of the correlator of endpoints, the endpoint correlator. Right? So the derivatives will just draw powers of iq. All the i's are concealed by the i's out here, and you get this path integral, right? Just using this. In the end, you set j equal to 0. That j goes away here. In fact, it should already have gone here because I'm not putting j equals 0. Right? And all the other terms that would have powers of j go away. Right? All that's left is this, and so it's very easy to get the n point function by doing this. Right? I'll quickly show an example now. I won't go through every calculation, but you should do it. Right? I'll go really quickly, just show the result, but you should do it yourself, right? Step by step. Let's say I'm interested in the 2-point function, so I'll take the second functional derivative of z. These derivatives work just like normal derivatives, so when I write z in terms of this definition up here, I can go with the derivatives inside, take this this path integral outside and act with these derivatives on the exponential. Right? Just like normal derivatives, since of course this will be a delta function times the partial derivatives of exponential we know how to calculate, so this is just exponential. And again, the derivative of what is here on top of the exponential. This part is just 0, the i's go away, right? And I have to act with this derivative on this integral right here. And of course then delta gt2 is just a delta function, and I can do this integral, right? Everything else is just repeating. I can do this integral, which will then give me this q calculated at point 2, which is right here. Then I have to do the other derivative, which again is the same. This derivative acting on this exponential will again drop integrals like that from the exponential. I'll have to derivate in terms of j, and I just get a q of t1, right? And the exponential again getting to this result. In the end, of course, I have to put j to 0, and j is only here at the action. I get the original action without this source. Right? I'm calling j the source for now, and I get the 2-point function. Right? So pretty easy. It's just the same as derivatives, but you have to remember the point of these derivatives is acting on functions, and then these scalar products go away, just like you would do with a normal product between two variables, right? This would be one variable, then another you take the derivative on the second one, you're left with the first one, but now you introduce the dependency on the points you differentiate in relation to at the start. So you're turning a functional in a function when you do that, right? You're extracting functions from your functional exactly as we wanted. Okay, so now that we have this introductory idea of what is a path integral and how to calculate these generating functionals and correlators using path integrals, let's try to apply that to a system that we know well, right? So of course the system we really know is the harmonic oscillator, right? And so we'll turn to that. Let's try to use path integrals in a harmonic oscillator to see what kind of information we will extract and what are the pitfalls, and that will also serve us as an example on how to manipulate path integrals, work with that a little bit. Right? So we start, of course, with the Lagrangian of a harmonic oscillator. Right? So there will be a kinetic term, right, which should be like that, but I'll just take this mass to be 1. The reason I'm doing this is because then the expressions will look more similar to the field version of it, which you have to be careful with. What is the mass? What is a mass and what is a particle in the field interpretation of this? So for now, just a harmonic oscillator with mass equal 1, right? And then I have the harmonic term here, which is just this, right? So of course, then we can go from this Lagrangian formalism to the Hamiltonian formalism, just taking the Hamiltonian and doing the Legendre transform, which would be this, given that P is just del Q dot, which is Q dot, of course, right? And so if I put this in here, I get that the Hamiltonian is just P square plus omega square Q square, where omega is the frequency of this oscillator, right? And so we know how to do this in the canonical formalism. I want to quantize this, right? And we know that in the canonical formalism, the way to do it, I'm just reviewing really quickly this to set the notation and have everyone on the same footing, right? The way to do it is to define these two variables that will become the creation and the annihilation operators once I quantize the theory, right? So I can define this A, which will be 1 over square root of 2 omega q plus IP, and I can define a dagger, which will be 1 over 2 omega q minus IP. Right, before I quantize, a dagger just means the complex conjugate, but we know I'll eventually make these into operators, and then will be A and A dagger. Actually, my dagger looks very much like a plus, so I'll try to be careful about that and make a proper dagger. Of course, I can go back with these two expressions, invert to get P, the expressions for P and Q in terms of A and A dagger. That's easy to do. I won't do it carefully here. I mean, everyone knows this. So P is just minus I square root omega over 2. A minus A dagger. And Q is 1 over square root of 2 omega A plus A dagger. So fine, and then I can go with these two expressions, just substitute P here, Q there, right? And rewrite the Hamiltonian in terms of A and A dagger. Right? And that will be, of course, I'm being careful of not commuting A and A dagger, because eventually I'll make them into operators. So if I don't commute them, it's this that I'll get if I do the substitution properly in the Hamiltonian. And this is the harmonic oscillator Hamiltonian. So the dynamics of this still classical oscillator, right, is given by the Poisson brackets. Right? So if I write, just to define Poisson brackets, right? If I write two functions, any two functions, there are functions of the coordinate of the system and the conjugate momenta. I'll say f of P and Q, and another function G of P and Q. Then the Poisson bracket between these two functions is defined as, I'll put a P, B here, Poisson bracket, just not to confuse this with an anti-commutator. This is defined as the sum over all the coordinates of the system of del F, del Qi, del G, del Pi, minus the other way around. So del F, del Pi, del F, del Qi. So this is the Poisson bracket. And the reason this defines the dynamics of the system is because the Hamilton equations can be written in terms of the Poisson brackets, right? So if I write that Q, so that any dynamical variable of the system will evolve according to the Poisson bracket of the variable with the Hamiltonian of the system. And the same for the time derivative of p. If I calculate these two Poisson brackets for the one with the coordinate, I get del qi, del qk, del h, del pk. Right? This is just a Kronecker delta, ik. And the second part is 0 because del qi, del pk is 0. So this is 0. And it doesn't matter, there's also a del h, del qk here. But in the end, I just get del h, right? I use this Kronecker delta with the sum. I get del pi, which is exactly the Hamiltonian equation we used to, right? Q dot I equals del h, del pi. And the same here. I also have a sum over k. Get some more space here. In this case, the first term is 0 because del pi, del qk is just 0. Del h, del pk. And now the second term is actually del pi, del pk, del h, del qk, which now is different from 0. Oops. This is just Kronecker delta, ik. I can use the sum over here to write this as minus del h, del qi. Right, which is, again, the Hamiltonian equation for pi. So everything is set by these Poisson brackets. And that's basically the setup I need to do the canonical quantization. We'll do that first. So let's think about the canonical quantization. The canonical quantization of this harmonic oscillator, right? So now, to quantize means to exchange these Poisson brackets by commutators, which makes Q and P into operators. So essentially, my dictionary is doing this. I would exchange Q by the operator Q, P by the operator P hat, and the Poisson brackets between any two quantities will become minus I over H bar, the commutator between those two same quantities. Of course, H is equal to 1 for us, so goodbye H. H bar actually. But we can just apply this dictionary to what we had before. So the Poisson bracket between P and Q, that one I didn't calculate explicitly yet, but I can quickly do it now. It's just the sum again over K of del Pi, del Qk, del Qi, del Pk, which is 0. Right, both of these are 0, minus del Pi, del Pk, del Q. Actually, there was a J there, so the Q is just Qj, Qj, del Qk. And the same is there's a Kronecker delta here, Kronecker delta here. I sum over K, I get just, there's a minus there, minus del Ij. Right? That's the Poisson bracket. Now that I am quantizing the theory, I just exchange the Poisson brackets on this side by following this dictionary, right? Minus I commutator of pi qj, and that should be minus delta ij, which of course I can do a little simplification, just throw this minus I to the other side, and I get minus I delta ij, which is the commutation relation between momentum and position, right? Which is what we would expect for a quantized system. Then I can bring those definitions of P and Q in terms of A and A dagger. Right? I can just take these two expressions, plug in here, and that will take me, I'm not doing that calculation here, but everyone has done it, at least I hope many times, and that takes me straight away to these. Now A and A dagger are operators, and that will get that the commutator between A and A dagger is just 1. I do the same in the Hamilton equations. These two, let me box this formula too, and I use the same procedure, right? Changing the Poisson brackets for commutators in the two Hamilton equations, which I'll copy here. This one now will become just minus I commutator and of course now we prefer to write these as del Q del T, and the same is for the momentum, del P del T is equal to minus I P hat H hat. Let me put hat everywhere, which is the one fact that we know that the evolution of the system is of the evolution of operators is given by their commutator, if the Hamiltonian, right? You solve this, you get the time evolution for these operators, which is just again coming from applying that dictionary between the classical theory and the quantum theory, and this is what we call canonical quantization. So just to remember some main consequences of these of quantizing the harmonic oscillator, right? We can rewrite the Hamiltonian. If you remember well, I had already written that the Hamiltonian was just A dagger plus A dagger A. I did that a few minutes ago. I can use this commutator to rewrite this as just 1 plus A dagger A, and have that I put that factor half inside, and I get omega A dagger A plus a half, right? Which is should be a very familiar expression for everyone. Maybe the one unfamiliar thing here is the lack of H bar here, but again, remember, I'm making this guy equal to 1. That's all. Right, so now my energy is just equal to the frequency. In this system of units, I just measure energy in terms of frequencies, the same, right? And we know that if I look for the eigenstates of energy, the eigenstates of the Hamiltonian operator, these guys will be able to write these eigenstates in terms of one number, right? We have a number operator, which is a dagger A, which we call the number operator, and I can take eigenstates of this operator with number n, and these two operators will have the ability to increase the number and decrease. So they're creation or annihilation, or ladder operators. They go up the ladder, they go down the ladder. So there's a whole set of states that is just numbered by these by the eigenvalues of this operator, and with some normalization. So every time I apply a dagger, I increase n by 1. Every time I apply a, I decrease this by 1, and this a and a prime here are just normalizations that I need to keep these normalized, right? And we know, again, we know those we know how to get those normalization factors, and a dagger a applied to n is just n, right? And n is the number that I can use to number all the states, right? Of course, if I keep applying the one that lowers the energy of the system, so the energy is proportional to the number, right? I can increase those states by increasing the number n, right, which is we'll call for now the number of excitations I put on the system, right? But if I lower, there should be a lowest lying state, which is defined by these equations, the one where you cannot go down anymore. So if I apply the going down the ladder operator, right, the annihilation operator on this state, which I'm naming omega, this goes to 0, right? So there's no state below that one. And then by definition, if I look at the definition of n, that means this is the state which has eigenvalue 0 to n. In other words, I'm calling omega the state with n equals 0, right? And this guy will be very important, right? Because I see a lot of confusion around this, but this is this lowest lying state that I cannot remove anything from is what I call the vacuum of my system, right? So this guy right here is the vacuum of my system. And then the energy can be written in terms of states created on top of this vacuum. And there is, of course, as we know, a 0-point energy, because if I apply h to n equals 0, right, I will just have energy 0 on this omega, right? Let's call this omega. Which is just this part, right? This will be 0, and I have omega over 2, which is the 0-point energy or vacuum energy. And for one oscillator is just this. Of course, I can exchange the the Hamiltonian, right, by imposing a normal ordering. So I can define the Hamiltonian in terms of the normal ordering of the previous one, right, which would be just A dagger A, right, where normal ordering means if I take the normal ordering of A dagger A plus A dagger, that would give me just A dagger A plus A dagger A, which is 2A dagger A, right? And in this case, the energy is just omega n. And that does not change the classical theory, right? I'm just changing the quantum theory to count energies starting from the 0.1. So I'm not taking into consideration the 0 point energy anymore. And that gets rid of the 0 point energy, which is fine. So this is canonical quantization. Let's see now what happens if we go to what can we see of the harmonic oscillator when we do quantize it using path integrals. In fact, we get a better view of what of all the subtleties and details that appear in the path integral if instead of treating the harmonic oscillator, we'll go to the forced one, right? It's more general because, of course, you can always take this external force acting on the harmonic oscillator to 0 at the end, and that will lead you back into the harmonic oscillator, the free harmonic oscillator, but also it's very convenient because remember I have defined this generating functional as the path integral over q of the exponential of I times the action, right? This action with a j here, where the action was this s of q j was actually just s of q, whatever was the action of the system, and plus this extra term that I introduced when I was defining the generating functional. And then when I want to extract from this generating functional the correlators, say the n point correlator from T1 bar to Tn, I mean these n points, this capital N, I just do the derivatives in all these j's, T1 bar Tn bar of z of j, and then I take j to 0. So j here was kind of this auxiliary function that I was putting in, and at the end I make it go to 0, so it disappears. It can be left without any physical meaning. But actually, if you look closely, right, I can also give physical meaning to this j, because suppose I take this action to be the action of my system, right, including this j, which I can interpret later, right? Then the extreme action principle will tell me that this equal to 0 gives me the classical solution for the system, the classical trajectory for Q, right? But that, if I use this expression, can be written as the variation of this action that just depends on Q, so this part, right? Plus the variation acting here, right? And this variation acts just like a functional derivative. So this functional derivative acts on this Q. I just exchange my variable by whatever variable this guy depended on, t here. So I just change this one inside the integral to a t prime, do the derivative, use the delta Dirac, and then I get j of t, and this is equal to 0. So I got a movement equation here for Q. I still need to know what this action is to go further. Well, suppose this was the harmonic oscillator. So a classical harmonic oscillator would have a Lagrangian, which is half. Again, the same one I used before, mass is 1. Q dot square minus omega square Q square. And if I plug that in here, I'll get an equation which is omega square Q minus Q dot dot plus J of t equal to 0, which is a forced harmonic oscillator, right? In this case, it's pretty clear what J is, right? Let me put here. Forced harmonic oscillator. And in this case, this is any external force that is acting on my oscillator, right? I can just put an oscillator suffering some external force, and this will be the movement equation for it. It's important to realize this. J of t here has no dynamics set by these equations. It's just external, it's fixed. So I know the behavior of this force acting on the oscillator, and I will solve this equation to get how the oscillator behaves according to this J of t. But that gives us yet another insight on what these correlators are, right? Since the correlators are obtained when I set J to 0, the correlators are obtained, they are encoding the behavior of the system in the absence of external sources, right? External forces in this case, right? So now I know that even J can be used to parameterize some behavior external to the system, right? Important to know that I cannot solve these for the behavior J. J is fixed, is a function of some force that can be constant, and it is not a function of time, or can be varying in time, whatever situation I have in mind, right? Now, the beauty of the harmonic oscillator, as we know well, is that this Lagrangian, and therefore the action, are quadratic in Q, right? This is just Q square here. And that means we have a hope of actually doing the path integral in Q, right? Before, we already did that with the path integral in P, because in that case also the exponential was just a Gaussian, right? We had just a Gaussian function here, and now the same happens for Q. So this is, again, that's the reason we do the harmonic oscillator all the time, right? Because we like to integrate Gaussian. So let's go forward with that. So I have to rewrite the action in a more convenient way. So I will stick with the forced harmonic oscillator. So my action now is given by the integral in time of the Lagrangian, this Lagrangian here, which is half let me write it like this: del q del t square minus omega square q square over 2 plus jq. Everyone here is a function of time, right? I'm bringing the integral of time outside, and that's the action. So now I want to write this in a quadratic form, an operator acting on quadratic forms. In order to do that, I want this derivative to be written, which is now is just del q dt del t del q del t, which is just, I can use this integration by parts, right, and write this as del t of q del t minus integral of q del 2q del t2, and this is a total derivative which I can just exchange by the values at extremes, which I'll assume to be 0. Right? And then I go up here, integral of time will be now minus half, this minus is what's showing up here, of q del 2 del t2 plus omega square, which comes from this part, and the minus is out here, acting on q. So now I have a quadratic form with an operator in the middle, which is very good to use that formula of Gaussian integral we had before. And of course there's this linear term on q, which you also know how to deal with if you remember the Gaussian formula from the last video. Right, so that's the form you want to integrate. Actually, those of you that are attentive issue with might be taking issue with this, right? And there's actually a problem here. But if you don't like what I just did here, and you said, well, that's not so trivial to assume that infinite past and infinite future these q's or the derivative will be 0, you're right about this. So, but let's pretend we didn't see this problem, right? That we can actually do this and go forward, and let's see how that would create problems for us, because this problem will show up again and again and again in quantum field theory in very subtle ways, and I want everyone to see when you don't pay attention to this what happens, and then we'll fix it, right? Because then we'll be able to see very general ways of fixing it instead of actually just fixing it for this case. So for now, let's pretend I'm doing the right thing. Be careful, the conclusions that will follow will have problems, but just bear with me here. So now that I wrote in this way, my path integral can be just written, right, as z of j is equal to the path integral of the exponential of minus half q delta minus 1 q plus I j q right, and pay attention to this scalar products that I'm writing here, right? They have a meaning. They are actually this. Actually, there's no dot here. This is just this, right? And this scalar product means nothing but the integral, right? So this is just the integral in time of j, t, q, t, right? Same here. And delta minus 1 is just I del t2 plus omega square, which is this operator that is acting on the space of these, in the vector space of these functions, right? We're dealing with vector space, so this operator is acting on Q. This is just a scalar product between these two vectors, which are in the space of functions, right? In real functions, for now. So now we can compare this with this formula we had for Gaussian integrals we have shown before, which is just this one, dnx of the exponential of minus half x transposed scalar product ax plus b transposed scalar product x is equal to 2 pi n over half determinant of a minus half exponential of half of b transposed dot a minus 1 b. If compare this with that, we can do just the mapping that b is minus ij t and a equals delta minus 1. Right? If you worry that here I'm doing a discrete vector space and here I'm doing the space of functions, right? Again, this is the transition we're doing every time. You can just discretize these variables, turn this into a sum and a product of integrals, and you get a very big, very long vectors, but then you do use this formula as normal and go back to the continuum. You might worry, what's the determinant then? And we'll deal with all of this later, but for now, whatever is the determinant, it goes into that same normalization factor that we always have, right? Because this determinant will not depend on j, right? All dependence on j is here, and so z of j will then be differentiated in j, and these numbers, which again, same thing we had when we integrated over p, there's a divergent normalization factor in front that will go away when we normalize for observables, right? So this determinant is just another product, very long product of numbers that will become some divergent thing that will go away once we take care of the normalization. Right, so z of j now is some n prime. Is not the same I had with the momentum path integration, but I'm putting in here the determinant of delta minus 1 to the minus half. That should be there, right? And since that does not depend on j, I'm not too worried about it. And this term is just what is left that it really depends on j, so I have to substitute it here and have minus half of j scalar delta j. And now there's two scalar products here. So just to be clear, j delta j is equal to where this delta is just the inverse of the delta minus 1 that I define here, right? And I can actually find this inverse by an ansatz, right? So I know delta minus 1 delta of t prime needs to be delta of t minus t prime. That's what the inverse means in this space of functions, right? So I have to find a function that when I act I del 2 del t2 plus omega square on, I'll get these, and the ansatz I can use for that. It's pretty obvious once you see it working, right? Is this 2 pi exponential of minus I p t minus t prime p square minus omega square, and this is my ansatz for delta of t and t prime. Right? And you can see that it works because once I act with these derivatives on this exponential, I will draw powers of p. So this will be this I, and this one will get me a minus 1. Let me keep the integral here, right? And I have this denominator which does not change coming from here, but the derivatives acting here, right, will get down powers of I'm differentiating in this time here, so I'll get minus IP square, right, which is minus p square, right, plus omega square, and I keep the exponential, right, minus e minus IP t minus t prime up here. Of course, these two cancel each other, right? With the exception of a sign that goes out here. And then I have just a definition of a Dirac delta, which proves I have the right, supposedly I have the right function, right? And so in principle I have the answer, right? I have my z of j, there's no path integration anymore, and I know who is delta. Seems fine, right? I actually got an answer, depends on some crazy big number here, but goes away as we normalize things. And this exponential for which I have obtained delta. Everything fine, right? Except not, right? Except it's not fine, right? Because this function here has a fairly diverging denominator here. If I'm integrating over p, the moment I take p square equals to omega square, this has a singularity, right? Is that a serious problem or not, right? We all know that we can go to a particular prescription in the complex plane and go around these singularities, but why is the singularity showing up in the first place, right? Have we done anything problematic here that could have avoided the singularity of appearing from the start? Or in other words, of course I can put an I epsilon here and circulate these singularities. We'll see how to do that pretty soon, but if I did everything consistently, shouldn't this I epsilon showed up here when I'm doing this integral, right? One way of seeing what the problem is here is by looking if this essentially what I did here, the main step I had to do in order to apply the Gaussian integral was to invert this operator, right? I call it delta minus 1, already assuming it would be inverted, because you don't call some operator delta minus 1 unless you're really interested in the inverse, which is delta. Right? So when I called this operator delta minus 1, I was assuming I would be able to invert it, and I did. I mean, I found by ansatz some inverse, but the inverse is singular. Right? It's written in terms of an integral that is not well defined as it is. I have to put some epsilon, some limit of the epsilon going to 0, so that's bad, right? That's not perfect, right? And you can see why, right? Such a problem would arise if that operator was not inversible in the first place, right? Suppose this operator is singular. If this operator is singular, I cannot invert it. How can I see if it is singular or not? Well, if an operator has eigenvalues equal to 0, so if I take that operator, and remember, those operators I'm writing here are acting on this space, this vector space of functions. So if there is a function, Q's, let's call it Q naught, for which this is true, then I found vectors in this vector space which are eigenvalues of the operator. This is delta minus 1, right? Which are eigenvalues of that operator with eigenvalue 0. And that means that an operator cannot be inverted. It's singular operator. And in fact there is, right? We know how to solve this equation. This is just the classical solutions to the free the harmonic oscillator, right? Without not the forced one, right? So I'm sure these guys exist in the space of functions. So this operator is singular, right? I have to be careful about inverting it. It's just not something I can do as naively as I have just done. I have to be real careful about this. So I think this is enough for today. What we'll do next video is try to fix this problem. So we'll see what needs to be done with the boundary conditions, because you know we're talking about this path integral and I'm always writing it like this, but I have really to specify, right? I'm taking all the paths between 2 points. So there are points here that I have to talk about and say what happens at these 2 boundary conditions of my path integration, right? And we'll see what we have to do with these boundary conditions in order to fix these, to make these valid. And then we'll see that proper boundary conditions will take care also of this problem by essentially removing these functions which are eigenvectors with eigenvalue 0 from the space in which this operator is acting. And in that way, this operator will be inversible. But this is very subtle, takes some time, so we'll do it on the next video. For now, what you can keep in mind is we have a provisory answer for the problem. I mean, a provisory generating functional, which is given by this with this operator. We'll see how that changes. There will be new contributions to this once we fix properly the boundary conditions. So see you next lecture. The exercises for today's video is just fitness for the brain. So what we're trying to do here is to develop your muscles of doing functional derivatives of this sort, of the sort that will appear all the time in quantum field theory. So having these functional derivatives acting on generating functional. So that's pretty much it. You have to differentiate these and set j to 0 at the end. But if you're really smart, you can already select which terms will survive before setting j to 0, and that's what you can probably figure out by trying to do this exercise. Good luck.